just over 5% of the time, and so forth and so on. Oops, I jumped one. I jumped one. I jumped one. Jeez. 136 to 236.
I thought you were doing that in your head. Yeah, she's good.
No, the TI can handle math in line, which is nice.
I just looked at it. I was amazed at Kathy.
Well, I know the problem is I'm talking while I'm working, so it's always a bad idea. 236.
That's beautiful.
There's your perfect isosceles triangle, if you were to graph it. And you'll notice that even though we are running empirical, this is a purely theoretical distribution. We got this via analyzing what the two dice could actually do. But when you compare it to what's showing up here, look, even though that's experimental, this is experimental, compare the decimals. You guys are getting 2.7%, right? 2.7% in your 2 and 12. 2.7%. Look, 3%, 3%. You guys were getting, what, 5 point something percent for 3 and 11? 5%? 5%? Oh, just about 6. These are going to fluctuate because it's between 5 and 6. Next up was somewhere around 9%, I think. 3, 6, 9. 8 or 9%. You got a 9 there, you got a 9 there. And what you're going to notice is from 2 up to 7, they're going to increase by just about 2.7% or 3% from step to step. Because that's what's going on. 136, 236. You're adding a 36 each time until you get to 7, and then it backs away again. But what I'm really most interested in is the fact that this thing is beginning to follow exactly the shape that it's supposed to follow theoretically. Isn't that cool? You're not quite as excited as me, that's okay. There we go, Steve, thank you. But that's what's cool. What's cool is after only fewer than 10,000 trials, fewer than 10,000 trials, and you get that pattern to show up. What's the, friends, what's the average standard deviation? Well, the average you guys know already, don't you?
Are you supposed to run L1
I would.
and L2?
Yes, ma'am. You gotta run L1 and L2. Now, hold that thought. Thank you, Cassie. 30, 45 seconds tops. First of all, you know what the average is going to be. What's the average got to be? Without even, just looking at this, what does the average have to be? It's got to be 7, doesn't it? It's got to be. It's a perfectly symmetrical distribution. And the mode and the median and the average, because it's symmetrical, are all the same point. So you know that the average sum is going to be 7. You know that. Now, if you don't remember that, you can run one more stats. Now, Cassie asked a great question and made a great comment. The great question first was that, do I have to use the L2 with the L1? Your response is? Yes, you do. Because if you don't, well, we'll go back to what happens if you don't momentarily. But the quick and easy answer is, if you don't, the TI doesn't know how often to count each data point. If you don't, you're treating this as uniform, aren't you? If you don't include your second list, it's pretending each of these things, first of all, don't have probabilities, and they're each occurring one time. That sounds uniform, not weighted. So you got to tell it to use, I'm going to use L5 and L6 because that's where my data is. Okay? There. Now, one note, TI note. It says X bar up there at the top. The TI will always call these things X bars. Your job is to know that this is mu. And Cassie has answered how to recognize that this is mu. What don't you see up there, friends? Which standard deviation? The sample standard deviation. There's no sample standard deviation because this isn't the sample. What is
The population.
This is the entire population. How does the TI know that? Is it just that smart? No. There's a mathematical reason how it knows it. There's a mathematical. Do you remember back in the day? And you can say no, of course. But I made you calculate Ernie's sample standard deviation. Remember what we divided by? What quantity we divided by to get that? You could, of course, say no to this because it was like 4 weeks ago. N minus 1. Okay, don't worry about it.
Oh, that's been you.
It's been like 4 weeks. I know, it's been a long, long time. Right, the N minus 1 you divided by. Because the probabilities sum to 1, the TI is trying to divide by 1 minus 1 or 0, thereby coming up with an error. So, when you see this, No sample standard deviation, it means you put in a beautiful probability distribution, which means you have the entire population. Which means that right there is your standard deviation. That's lowercase sigma right there. Oops, that's lowercase sigma right there. That's your population standard deviation. So your plus or minus of that sum is about 2.4 plus or minus the 7. That's what that number means, that other little guy under S. I know you were getting him an awful lot before. Whenever you ran a sample, you were also getting him, and I told you to keep ignoring him. Because before you had samples, not the entire population. And I told you eventually we'll get around to talking about the population, and here we are eventually. Does that make sense-ish? Have I a question?
Well, I looked at the Q1 and median, and
Oh, good for you.
I decided it had to be more than 2 because 50% is only Q1 to Q3.
Nice, very nice, very nice. It has to be more than 2 because half the data is contained between 5 and 9. Very nice, my friend. Excellent, 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 excellent. Yeah, and you can use all those. I love to hear that because you can use all those cool old moves about outliers. For example, you could set up 2 standard deviations to find the outliers outside of 2 standard deviations. But there's something that's even cooler. There's something that's even cool and easier. And this is my favorite way of identifying outliers. And I told you there's dozens of these ways, dozens literally. But here, and we'll do this. Let's talk about it briefly now, and then come back after break and kind of analyze it. The best definition I've ever seen for an outlier. What is an outlier again?
It's overly different. Hold on.
I like that. I like that.
Unusually small or big.
Good, good, good. Just can I even make it more general if it's okay? I'm going to say it's an unusual data point. Can I just say that? Rather than small or big, just call it unusual. If that's okay, it just makes it more general. So an outlier, basically, I love the word unusual. I love that. It's an unusual, or if you like this better word, atypical data point. What do you think unusual means in a probability context?
It rarely happens.
That it rarely happens. If something rarely happens, is it going to have a high or a low probability? It's going to have a very low probability. I love that. If something rarely happens, it's going to have a very low probability. How do you define very low?
No, a third.
Good. Let's take 5 and think about that. As you're getting your air and your water walking around, think about what defines a low probability. I want a kind of a cutoff, like a guideline for when too low is low, or when low enough is too low. Think about that as you wander around. We'll come back and talk about it, okay? Michael, what you got?